All right, today we are going to look at work done by non-uniform forces. That means forces that change with respect to position. If it changes with respect to time, we're going to use a whole different method. But if it is a function of force dependent on position, this is the way we're going to do it. We're going to go the work method. So how do we find the work done by a force like this? So my example here is we got some holiday lights in a box. We're going to slide those holiday lights 4 meters across the driveway with a force applied of this. We're going to say that driveway is nicely icily covered for the holidays, and so we have no friction, just so we know this force actually causes it to move the 4 meters. So here we go. Let's apply that force function to our work equation. So our work equation, when we have a non-uniform force, is we need to take integrals. Now the important thing to note here is when we take our integrals, it is the x component of the force integrated in the x direction. The y component of the force integrated in the y direction. Now for us, we are going to solely focus on just one dimension at a time. We are not going to do multiple dimension integrals all at the same time, but this is how you would do it if you needed to. So let's try it out. So I have my box moving solely in the x direction, and it's moving from 0 to 4 meters. So that means to find my work, I'm going to take the integral from 0 to 4 meters of negative 2x squared plus 7x plus 4 dx, and the reason I can do this with dx is because this is my I hat component. Okay, everything's got to meld together, so my I hat component goes here with my dx with my x initial and final positions. This is a nice one because I can just plug this in my calculator and do the integral, and I come out with 29.3 joules of work for that variable force pushing that box of holiday lights 4 meters.